Okay, let's look at studying linear equations of the form ax plus by equals c. Later in the semester, we'll study systems of linear equations and more variables. So let's recall what we did last time, the GCDLC Theorem. So this was simply the statement that you can express the greatest common divisor of any two integers as a linear combination of the two integers. So if D is the GCD of A and B, then the equation ax plus by equals D has an integer solution. So we want to look at a more general equation where instead of having the greatest common divisor here, we put an arbitrary integer c and then ask when can that equation be solved. So let a, b, and c be any integers with greatest common divisor d for a and b, and consider the two equations ax plus by equals c and the companion homogeneous equation ax plus by equals 0. So you'll note by linearity that if we have a particular solution of 1, then the general solution of 1 is of the form xy equals the particular solution plus a solution xh, yh to the homogeneous equation too. So let's see why this is true, because if you just take these values here and insert it into 1, you'd have a times x0 plus xh plus b times y0 plus yh is distributed out. ax0 plus by0 plus axh plus byh. Okay, that's the particular solution. So that one adds up to c. And this is a homogeneous solution, so that adds up to 0, and so we just get c coming out. So we can always get the general solution to the non-homogeneous equation by taking any particular solution and adding on an arbitrary solution to the homogeneous equation. Okay, so when does the non-homogeneous equation have a solution? And the lemma we have is the following. The equation is solvable in integers if and only if the greatest common factor of a and b is a divisor of c. Okay, so this is an if and only if statement. So one direction is let's suppose the equation is solvable. Suppose the equation is solvable. So let x and y be integers with ax plus by equals c. And we want to show that d is a divisor of c. Well, d is a divisor of a, and d is a divisor of b by definition of GCD. Therefore, d is a divisor of any linear combination of a and b. That was one of the basic lemmas we proved right at the beginning. So d divides ax plus by. This is a linear combination of a and b, but that equals c. So d divides c. Conversely, let's suppose that d divides c, and we want to produce a solution to the linear equation? Well, by GCDLC, there exist integers x and y with ax plus by equals d. Aha! If we just multiply through, we should get a solution with c. So d divides c means that d times lambda equals c for some lambda. So I'll just multiply this equation through by lambda. Like that. And on the right-hand side, we have c. And on the left-hand side, I'll just rewrite it as a times lambda x plus b times lambda y. And that gives us the desired linear combination. So we have a solution to the equation with c on the right-hand side. And notice that lambda x and lambda y are both integers. So we have an integer solution. Okay, now let's turn to the homogeneous equation and characterize the complete solution set. So I claim that an integer pair xy is a solution of ax plus by equals 0 if and only if xy is some scalar multiple of negative b over d, comma, a over d, where lambda is some integer. Okay, proof. So we have ax plus by equals 0. So suppose x and y is an integer satisfying this equation. So that would say that ax equals minus by. Okay, now d is the greatest common factor of a and b. So let's divide both sides by d. Like that. Now a over d and b over d, those are integers because d is a divisor of both a and b. And this equation is telling me that a over d is a divisor of b over d times y, this product. But since the GCD of a over d and b over d is 1, right, we've divided out any common factor. By Euclid's lemma, we get that a over d is in fact a divisor of y by Euclid. And that means that a over d times some lambda equals y for some integer lambda. And then once we have that y is this, it's routine to just come back up, say, to this equation here and solve for x. So x is minus b over a y, which is minus b over a over d lambda. The a's cancel and we get minus b over d lambda. QED. So xy is exactly of this form. X is lambda times minus b over d and y is lambda times a over d. Now for completion, we should also note that any xy of this form is certainly a solution. So if x is lambda minus b over d and y is lambda a over d, then xy satisfies the homogeneous. Oops, got to squeeze that in. The homogeneous equation. Okay, so now we can put everything together and come up with a general solution. So remember, the solution to the original equation 1, the inhomogeneous ax plus by equals c, we said can be obtained by taking any particular solution and adding to it a solution to the homogeneous equation. So if we put all this together, first of all, we observe that 1 is solvable if and only if d is a divisor of c, d is the greatest common factor, in which case we claim that the general solution of 1 is of this form. We take a particular solution, and it can be any particular solution, and we add to it the solution to the homogeneous. So this is just putting together the observations we've already made. So this is particular, and this is the homogeneous solution that we just saw in the previous lemma. Now let's look at the geometric point of view here. So solving the equation 1, which I've written again right here, is equivalent to finding all integer points on this straight line, ax plus by equals c. So we have some line in the plane. Maybe like that. And then we have some particular solution on the line. This is your x0, y0 point. And remember, these are the points with integer coordinates. So we're not looking for all of the real numbers on the line. I just want to know what integer points the line happens to pass through. And so our theorem says you start at a particular solution and you add any integer multiple of this direction vector. So what is this direction vector? It's minus b over d, and then a over d. Well, I've got to keep it in the same direction as the line I'm drawing right here. So it's going to be like that. A over d. Okay, so that's the direction vector. Let's call it v, the direction vector. And it has integer coordinates. Okay, so I can go up this distance, v, like that, or we can subtract multiples of it and come back that same distance. So this would be minus v. And then you can take another integer multiple, and then another multiple of it, and another one. So how did I get down to here? I took the initial point and I subtracted 1, 2, 3, 4 v's. And so you get this set of discrete points on the line. And that characterizes, remember, all of the integer points on the straight line.